Hi, today we'll be solving a new problem. This is problem number 4 from 2017 AP Calculus AB free response questions. It's a very interesting problem because we see for the pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0. And the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies the differential equation dh with respect to time is negative 1/4 times h minus 27, where h of t is measured in degrees and h of 0, so the initial internal temperature, is 91. Let's see what should we look for in this problem. There are 3 subpoints. A, we need to look for the equation for the line tangent to the graph of h at t equals 0. And we have to use this equation to approximate the internal temperature of the potato at times t equals 3. A second subpoint is to use the second derivative of h to determine whether the answer we found at part subproblem A is an underestimate or an overestimate of the internal temperature of the potato at times t equals 3. And C is actually where we have to solve a differential equation. So for t less than 0, there is an alternate model for the internal temperature of the potato at times t minutes. And the function g satisfies a differential equation, which is C. The derivative of g with respect to time is negative g minus 27 raised to 2/3, where g of t is measured in degrees Celsius as well, and g of 0 is 91. We need to find an expression for g of t, and based on this model, we need to find the internal temperature of the potato at time t equals 3 minutes. So somehow, if we can, we'll compare this value we find for the internal temperature with the function g at subpoint C with the estimate at subpoint A. Now, before moving on solving this equation, we might need actually to do a little bit of review of the things we will be working with. So let's see what shall we do right here. For the first part of the problem, subpoint A, it would be a good idea to put the notes down and let's figure out how should we solve it. Just wait a little bit until you'll see my notes. Here are my notes. So we'll be starting basically with writing down what are, looking again over the problem and writing down what will be the data I need from this problem. So I'm writing now immediately what is going to be the equation for the internal temperature. So let's see it. The H, which is the internal temperature, is going to be given by the equation dH with respect to time equals negative 1/4 times H minus 27. So I'm going to write it down now. Do not forget the temperature H of t is measured in degrees Celsius. And now let's see what are the other conditions given to us. There is an initial condition. It says the internal temperature of the potato was 91 degrees at time t equals 0. So h of 0 should be 91 degrees Celsius. And there is a second piece of information. The internal temperature of the potato is greater than, if you look right there, is greater than 27 degrees Celsius for all times t greater than 0. I insist right here that time is measured in minutes. So I'm writing that condition as well for time greater than 0. Now, let's go to solving the first sub-point of the problem. So let's find the equation of the tangent line to h at the point x t equals 3. So let's put in general right here, how do we write the equation of a tangent line to a graph h when knowing the function h and when knowing the point on the graph where the tangent line is intersecting the graph, so x sub 0, y sub 0. If you remember, this equation is actually y minus y sub 0 equals m times x minus x sub 0, where m is the derivative of h with respect to time at this t0, x0, t0, however you want to write it. Because our function h is as a function of t, I will put t0. So the derivative of h with respect to time at t0. In our case, at t equals 3 minutes. Now let's do the work. And notice that the derivative of h with respect to time is already given to us. So I can find out actually the slope right away by using that differential equation. So m is negative 1/4 times h minus 27 at times t equals 0. I'm sorry, I said earlier time equals 3. At time equals 0. It means that for h, I have to take h of 0, so that's 91 degrees. 91 minus 27, I believe, is 56. 56 divided by 4, it seems to me it's 9. So m is negative 9 degrees Celsius per minute. So I think I wrote seconds right there. I'm going to correct it later. So I have actually the slope, I discovered it, is negative 9 degrees Celsius per minute. Now I need x sub 0, y sub 0. And using those coordinates of the point on h, I can write the equation. X sub 0 is 0, and h sub 0. So on the graph, I have the point h sub 0, which is the initial condition, is 91 degrees. Now I have the coordinates for the point, so I can write actually the equation of the tangent line at point 0, 91 degrees. Y minus 91 equals negative 9, that's the slope, x minus 0. We can write this one as a function of y, so y equals negative 9x plus 91, and this is the equation I have for the tangent line at the graph at point t equals 0. Now the second part of the problem is to approximate the solution of h of 3 by using this, that's what they say, use this equation to approximate the internal temperature of the potato at times t equals 3. So to find out with approximation h of 3. Let's write, instead of y, f of x. is negative 9x plus 91, and I will evaluate f of 3. I get 56 degrees, 56 degrees, and this will be the approximate value of H, internal temperature, at time 3, where 3 is 3 minutes. Yeah? Okay? Good. Now, if we are okay with this part, let's check out our solution. We have it right there. We have the equation, so we got actually all the things we were required to figure out in A. The equation of the tangent line and the value of an estimate using this equation for H of 3. Yeah. So how did we solve the problem? Well, lots of things are already given to us, like the derivative of the function with respect to time. We use that one to find out the slope. Then the initial condition helped us to figure out where the point is located on H. Let's move now to the second part of the problem. So for the second part, we need to use the second derivative, d squared d2 of H with respect to time, d2 squared, to determine whether the answer we got on part A is an underestimate or an overestimate of the internal temperature of the potato at time 3. So before moving right there, we will need a little presentation. So at this point B, let's see if we can establish the relationship between the concavity of a function, so the sine of f second, and the estimate given through evaluating the tangent, the value of the tangent line, I mean, not the value of the tangent line, the value of y given by the tangent line equation to the graph of f at a certain point. Yeah. So I will use graph in order to illustrate actually our point. So to see how those estimates are comparing to the real values. So let's say in the first situation, we have the second derivative of the function is positive. Therefore, the function is concave up. Now, whenever I'm talking about functions that are concave up, let's have in mind a model like y equals x squared. So that's a good one to illustrate what is going on. On this equation, let's assume that I will choose a point on the graph that corresponds to a point P that corresponds to a certain value x on the x-axis. And I'm going to draw the tangent line at the graph through that point. So let's see if that's the x value I'm using in order to estimate the f of x by using the tangent line equation. And in order to find out the real value, obviously I should have evaluated f of x. Yeah, I can notice right here that something is going on. So if you look at the graph, you notice that this tangent line, which is the tangent line to the graph, is always underneath the graph of the function. So the estimate I made right here, I figure out, is always less than the real value of the function. It means that if the second derivative is positive, so the function is concave up, actually through a tangent line, I have an underestimate of the value of f of x. Yeah. And the reason is because however you draw a tangent to that graph, you've seen on the left side of the picture now, always that line is going to be underneath the graph. So the tangent will be always underneath the curve. So let's see now the second situation, when f second of x is less than 0. Because on that situation, I have a concave down function, and always have in mind for this the function y equals negative x squared. That's an easy model to keep in mind. So we'll do reasoning similar to the one previously done. I will choose a point x on x-axis. Then I have that point on the graph. It's marked by an x, through which I will draw a tangent line. So let's take a look now and see what's the estimate. The estimate of f of x, so that's that estimate e of x I put. And on the left, I have the real value, f of x. Notice that the real value of the function in this situation is less than the estimate. So I will say that because of that, the line tangent overestimates actually f of x if I want to use it to approximate f of x. Notice also that in this second situation, the tangent line is always above the graph. So always any estimate will be higher than the real value of the function. Yeah. Compare those two, and I think now we can move actually to try to solve the point. Since I have to figure out how is my second derivative. If it's positive, then it's easy for me to decide. If the second derivative is negative, then also it's easy to decide. So I just have to evaluate. I need to find out the second derivative of h with respect to time. So that's actually the real question. Well, I don't have h, but I have its derivative. So let's write it down. The derivative of h with respect to time is the equation given to us, negative 1/4 times h minus 27. Okay, let's differentiate this whole equation with respect to time again. And I will write it immediately down. The derivative with respect to time of the derivative of h with respect to time will be the derivative with respect to time of the right term, which is the expression negative 1/4 times h minus 27. On the left side, I have exactly what I'm looking for, the second derivative of h with respect to time. On the right side, I will use the distributive property of differentiation. Notice that negative 1/4 is a constant, gets outside of the differentiation process. And the derivative of h with respect to time is the h with respect to time. The derivative of negative 27 is going to be 0. So that's not part of my equation. And I'll say, hey, but what should I do now? Where do I take the h with respect to time? Well, that's the equation that's given to us. So I will replace the h with respect to time with its expression, which is negative 1/4 times h minus 27. Let's see how the work is moving on, and let's see if this expression is positive or negative, or maybe a combination of both. So do the substitution. That will be negative 1/4 times h minus 27. Multiply negative 1/4 with negative 1/4, we end up with 1/16. So the second derivative of h with respect to time is 1/16 times h minus 27. Now remember from the condition of the problem that the internal temperature of the potato, let me show you right away, I will underline that thing, that information, so the internal temperature is always greater than 27. because the internal temperature is always greater than 27, it means that H minus 27 is going to be positive because H is greater than 27, yeah? So now let's see how is the second derivative. Well, it's a product between 1 over 16 and a positive quantity. The second derivative is going to be positive. I'm going to write this one down. So I know actually now that I am on the first situation I have described earlier. My estimate of the function given by the tangent line will be always an underestimate because the tangent line, it's always underneath the graph of f, whatever is that function. As long as the function is concave up, any tangent at any point for the interval where the function is concave up, the tangent will be below the graph. So the estimate is an underestimate. It's lower than the real value. I'm going to write this one nicely here. And that actually should conclude our second part. So since H is concave up, and I put all those I will say explanations, I can write down nicely. The estimate through the tangent line of f of x is an underestimate. And I put again any, so I will write now immediately, any tangent line to the graph of f, or h in this case, is below the graph of h. So that's a good part of information that we need to add in order to support our choice for the solution. So again, I need to make that observation. It's a good piece to have in mind, these two graphic representations of underestimate and overestimate. So let's write down in a parenthesis that fact. So because the function h is concave up, I would say any tangent line to the graph of h is below the graph of h. Okay, and now we get to the meaty part, to solving a differential equation. And we'll take a look at the problem. We'll read it again. So right here is for the type t less than 10. The alternate model that satisfies that equation, the internal temperature is given by a function g. The derivative of g with respect to time is negative, parentheses g minus 27 raised to 2/3. And g of t is measured in degrees Celsius, and g of 0 is 91. So it's identical the initial condition with h we had earlier. Find an expression for g of t based on this model. So we need actually to integrate to get the g as a function of t. And then based on this model, use the internal temperature of the potato. What is the internal temperature of the potato at time t equals 3? So once I'll find out the model, I'm going to substitute t for 3. Now this new value I will get will somehow come up to be comparable in a way with the value I got at point A, where I had that estimate. So probably, I don't know, that estimate will be kind of, I know it's different than the real value of h, but because the real temperature of the potato seems to be described by g, definitely my estimate at point A should be, at time t equals 3, should be an underestimate. And g of t, it might be the real value. So let's start the work. Now, I know that for the time t less than 10, the function g is described by the differential equation dg with respect to time equals negative parentheses g minus 27 at the power 2/3. And here g of t is measured in degrees Celsius. I know as well that the initial condition g of 0 is 91 degrees Celsius. And what do I need to figure out? I need to figure out g of t, and I need to find out g of 3. So the internal temperature at times 3 minutes. Let's try to find out the solution of that differential equation. I'm going to use, as you remember, the separation of variables. So I will try to have all the variables containing g in, let's say on the left side, dj including, and all the variables containing the t, or representing t, on the right side, so dt including. It's clear that an easy way to do that is by multiplying the whole equation with dt over g minus 27 at 2/3. I'm just going to write what is coming out of that. So I'm not going to actually write down the multiplication. So when I'm multiplying with the fraction I said earlier, on the left side I'll obtain only dg over g minus 27 raised to 2/3 because dt and dt canceled out, and on the right side just negative dt. The next step after I separated the variables is to integrate on both sides. So let's do that. Integral of the left side should be equal with the integral of right side, which is negative dt. On the right side, I can figure out immediately what is that integral, because negative is a constant, -1, integral of dt is t, so negative t, and I will add the constant right there. On the left side, I'm going to write this such that, expression such that I can use the power rule. So I'm going to write it as g minus 27 raised to negative 2/3 dg. Now, let me remind you the power rule. So for the power rule, probably here I should work making a little substitution. Let's say u is g minus 27, but if you look like d u is the same as dg, doesn't make any sense to do the substitution. We can do it directly. So let's remember the power rule. Integral of u raised to n du is 1 over n plus 1 times u raised to n plus 1. Remember, I didn't put a c right there, another constant, because I added on the right side. Yeah, so doesn't matter. I'm going to write down now what I will get. So n is negative 2/3. I'll get 1 over negative 2/3 plus 1 times g at minus 27 at negative 2/3 plus 1 gives me 1/3. And that's equal with negative t plus c. So I will figure out now what is this fraction 1 over negative 2/3 plus 1. Negative 2/3 plus 1 is 1/3. 1 over 1/3 will be 3, so I can rewrite the equation as you see it right there. Now, to get c by itself, I need to use the initial condition. At time t equals 0, g of 0 is 91. So let's use it. I'm going to have then, let's substitute right there, 3 times, parentheses. Let's see, 3 times parentheses 91 minus 27 raised at 1/3 equals c. I don't know if my computations are correctly done, but 91 minus 27, I believe, is 56. Maybe not. I think it's 54, not 56. But anyway, Yeah, you should do the correction. So I got C equals, yeah, it's 54. C equals 3 times cubic root of 54. So please make a correction. I don't know why I put 56 right there. Who knows? 54. Okay. So let's take this equation and let's write g of t, because that's what I was looking for. So 3 times g minus 27 at 1/3 should be negative t plus 3 times cubic root of 54. My bad, I put 56 right there. And now I will get g by itself. So I'm going to raise to the third power the whole, I'll divide first by 3, I'm sorry. And I get plus cubic root of 54. And now, in order to get g minus 27 by itself, I'm going to raise to the third power. G minus 27 is that expression on the right, cubic root of 54, don't forget, to the third power. Now, just g of t, I will add 27 to that cubic factor. Cubic term, I'm sorry, negative 2/3, cubic root of 54, everything to the third power. Don't forget to the third power for the cubic root. And yeah, I will have that. So I still need to put the power right there. Now, you see the steps through which I just moved on. I need g of 3. Negative, I will replace the time by 3. So yeah, it's I'm correcting now and placing the exponent 3. So again, another correction right there, the cubic root of 54 plus 27. So please, this should be the real temperature if that function g describes accurately actually the evolution of the internal temperature of the potato. Now, one can take this value, which is kind of ugly, the cubic root of 56, it's less than 4. So I don't know. That will be a hard thing to figure out with... So I can do it with approximation. So I might get something that's close to 54 that I got earlier. But I think it's a little bit larger, the value, because the cubic root of, or maybe less, the cubic root of 54 is less than 4. Yeah. So maybe, no, I should get a higher value or a less one. The estimate with, do you remember what did I say the estimate was last time? Oh yeah, I had an underestimate, so I should get a larger value right here, whatever is that value. Now, you've seen a couple of errors I made, but one is I carried with me, that's the cubic root of 54. As you see, we discovered actually how to solve this differential equation. We separated the variable. We got g by itself. Then we got g as a function of t. Then we used that one to estimate the internal temperature of the potato at time t equals 3. Okay, that's the whole work. So I pointed earlier to the comparison between the result in point A and point C. The result in point A should be less than the real temperature of the potato. Now, what I'm asking you now to try to do, so we can see that at subpoint A, we discover something like a 56 degrees temperature, so probably that will be on our case a little bit larger. The next thing I will ask you to do is please take a look at all this work we have done. The preparation for subpoint B, this is a point to really make it. How we started solving subpoint C, the work we have done to get actually the whole equation, G of t. Separation of variables, it's one of the methods we have used, and our differential equations, the differential equation we have studied are all with separable variable. Please check the scoring guide in College Board for 2017 and do the scoring for these problems. Thank you so much for watching this, and please try to get ready. Come up with questions if you have regarding this subject. Okay, have a nice day.